In the previous tutorial, where we took care of avoiding jitter in a simulation, we just used a long piece of geometry of polyline as our initial wire. However, I was wondering how you'd go about simulating something like silly string, or just a wire that keeps appearing. And while this is one of those things that is pretty easy in grains, have a look at Matt Estella's CG Wiki, I will post a link, it turned out to be a bit more complicated in Vellum, as it offers more possibilities of creating and managing constraints than Grains does. So here is what we need to know in order to create our own kind of silly string in Vellum. We need to know two types of constraints that we will use. On the one hand, the distance, the length constraint that we already know. It just keeps the distance between 2 points. And in order to keep these 3 points here spaced apart, I will need two constraints. One between point 0 and 1, and one between point 1 and point 2. However, when it comes to bend constraints, which are an important part in strings and wire dynamics and hair, we have this situation. So to measure the bend across one single point, I need 3 points at all in order to specify the angle at which the primitives which connect to the center point meet. So a bend constraint in Vellum consists of 3 points instead of those simpler distance or length constraints, which just connect 2 points. With that in mind, here are the steps that we need to take care of in order to create our silly string emission. First and foremost, on the very first frame of our simulation, we need to create the polyline that is our silly string. And then each frame, we will emit a new single point, set this point's scale, and add this new point to this line that we created on the first frame here, and then create a distance constraint between the newly created point and the previous point. And after that, create a bend constraint between the new point and the two previous points. As mentioned before, a bend constraint always needs 3 points. And sixth, this is optional, pin a given point if it's settled to prevent jitter. Basically the technique that I've shown you in the last tutorial. So these are the, depending how you count, 5 to 7 steps that we need to set up in order to create our silly string. So in Houdini, let's drop down a geonode, dive in there, and let's use the add sub to add a single point. Just check this point here, and let's have it appear at 1 in y direction, like this here. Let's increase the point size to say 7, so we can see it a bit better here. Next, for my silly string, I want this to kind of coil up, so I want to move this point around in a circular pattern. And yes, there are multiple ways of doing that. I'm a fan of old school vex, so I'll just drop down a pointer angle and do a bit of trigonometry in here. So I'll just define an angle first, which is given in radians, not in degrees. And I'll just use our current frame and multiply this by 4. Next, I'll specify a radius, call it r, set it to say 0.25. Next, let's calculate the x and z position with the help of our cosine. Multiply it times r to get the radius, and do the same thing for z, just using the sine this time. And finally, write it back to our position with our y-coordinate set to 0.5. So I could have set this to 0.5 initially too. However, it doesn't matter, as I set the point coordinate down here in the pointer angle. So let's hit play and see how that works. And we have this single rotating point here. Okay, next let's add a bit of jitter to that circular movement just to make sure the points do not appear on the exact same position. Just to break up our simulation, make it look more natural. Let's dial in an overall scale of 0.01, and let's have a seed be driven by our frame number like this. So a tiny wiggle added to that rotational motion. Next, let's set up our point so it'll be recognized by Vellum using a Vellum constraint, which we'll set to be of the type string, which you want to use here. Let's also attach to this two nulls. Call one out underscore geo and the other one out underscore constr for constraints via the respective ports in here. Let's have a look at our constraint setting here. Set to string, primitives, triangulation is alternating. Let's give the whole thing a thickness. So the particle has basically a scalar radius. Let's set this to 002. Let's not touch the normal and tangent drag. We don't want to pin this to an animation. Stretch stiffness seems okay. And also bend works fine like this. So this is our basic setup. Let's clean this a bit by holding A pressed while having these nodes selected and then just moving our mouse up so it auto layouts in vertical direction. Let's drop down a .NET. Dive in there, and it's here where we'll set up most of our constraint and geometry creation. And while this is going to be quite an involved setup, the basic steps are quite simple. It just looks a bit messed up due to Dub's nature, or maybe the way I set this up initially. But let's have a look at it. Again, let's start from the bottom by dropping down a gravity, then wiring in a merge, where we first will merge in a static solver, which in turn will be wired to a ground plane. Like this. Let's uncheck display proxy geometry, move this to the side, and drop down our vellum solver, which will wire in the merge too. This one is a vellum object, and we don't want an initial geometry or initial constraints in here, so let's delete that. And as we're dealing with quite a few collisions and intercollisions here, I want to set up my vellum solver to involve 3 substeps and maybe 20 constraint iterations. And within the Advanced tab, let's set the maximum acceleration to 10. Now, the first thing I want to do is source vellum particles. So let's drop down a merge, as we're going to be wiring in different DOP nodes into our post-solve slot here. And let's start with a vellum source and set its subpath to point to our out geo and the constraint subpath to our out constraint. Let's set the emission type to continuous and leave stream and bindings as is. So let's just wire this in here and see what happens. So as soon as I hit play, I see quite a bunch of points appearing. And let's just enable point number, so let's skip 1 frame ahead. That seems to work. 4 frames, 4 points. But just to make sure, there are certain instances where these nodes that we're going to drop here will be evaluated not only each frame, but each substep. So with 3 substeps, some of those nodes that I'm going to drop here are going to be executed way too often. And to fix this, I will insert here a gas intermittent solve, which will take care of everything being above this node being executed only once per frame and not once per substep. So this simple point emission works. However, I want to stitch them together and tie them together as a polyline. So we have to create this first, but only once for our simulation. And I'm going to use a GeoWrangle for that, which I'll wire in before our source, our vellum source, so it'll get executed previously. And in here, I will run over the details only once, and we'll check if our number of primitives is smaller than 1, so if no primitive exists here in the geometry, then we're just going to create one using the addPrim command and adding a polyline, like this. Now that we took care of creating this polyline, let's add this newly added vellum particles to the polyline as soon as they get created using a pop wrangle. Again, vellum particles are just pops particles, and let's, just for readability's sake, wire those in a merge with the vellum source getting executed first and then the pop wrangle, and wire them into the second merge like this. So we're using the merges here to structure our setup. So after the vellum source created those particles in our simulation, let's, in this pop wrangle, add them to this newly created polyline here. And in order for that, it would be really nice to just have the newly created particles in a separate group called new parts, or basically anything. And this is a standard feature of the pop source node, for example. So in here, in the birth tab, I can specify a just born group, for example, new parts. And then the particles that are born just in this frame are automatically assigned into this group, and this group will always contain only the newly born particles, the newly created particles. However, our vellum source, for now, is lacking that functionality, so we'll have to hack it in order to provide it with that. So let's right-click on the vellum source, go to Allow Editing of Contents, do the same thing for the pop source, allow editing of contents here too, and let's dive into the pop source here. Dive in further into the sub solver here, and after a bit of searching around, we can see here we found the group node that is used to set the just born group, and here to remove them from the particles that are in our simulation but are not born on that very frame. So let's try and build the same thing in our vellum source here. Dive in there, we have a continuous emission, so we're going in here, and well, this spaghetti code is what the vellum source looks like currently, and what we need to do is create a group node, set this to points, call it in our case new parts for new particles, enable it, and just add anything in the stream to the base group. And that goes in here. Copy this here, paste it, and let's wire it in down here. and just set it up to delete anything that's in this stream and remove that from the group, like this. And that should be it. Now we created a just one group that is called new parts. I mean, you could wire this up onto the Vellum source directly, but I'm not interested in changing its name yet, so let's just go up. Let's hit play. Middle mouse on this. We can see in our point groups we only have one particle in the new parts group with 12 in our Vellum stream. That is super. So that works. Now that we figured this out, in our pop wrangle, let's check group, and in here only work on new parts. That's the single new particle we're creating each frame. And let's just add it as a vertex to our polyline using the add vertex command. Goes into our 0 input stream. That's the pop stream itself. The primitive number is 0, as we're only working on one single primitive with the primitive number 0. And we're going to add to it our current point number. So the new parts point number will be added. And that's it, just a single line. Let's save this and give it a try. We can see now we are creating a polyline connecting all these individual points, which slide around and don't look like a string or anything else, but at least they are connected now. Let's get rid of the pop source. And let's take care of creating those constraints with the distance constraint first. So I'm going to do that using a GeoWrangle. And I'm planning on using two GeoWrangles here, one for the distance constraint and one for the bend constraint. So again, let's drop a merge so we can group those together with the point wrangle that I'm going to use for the distance constraint going in here first. And then later I'll wire in the bend constraint in here. So let's wire up this merge too. And in my data bindings tab, this is always set up by default to run on my geometry. However, I want this to be executed on the constraint geometry. So let's set this one to constraint geometry with a capital C like this. And that's all there is that's needed in order to create constraints with the same GeoWrangle that we'd normally use just on our main geometry. However, what we also want is we want to access the main geometry and look up certain points and certain point attributes. So we'll have to set that up in the inputs tab here. With the input 1, that's our constraint geometry, still set at none, we just leave it as is. And the second input set to dop data, and either we can type in an expression manually or we can just steal it from the Vellum constraints property here, and in the inputs you can see it's this expression that we want to steal, $objid/geometry, which we're just going to paste in here like that. Let's delete the Vellum constraint property again and work on our geometry wrangle. So now our GeoWrangle is set up in a way that we are working on the constraint geometry mainly, but can access our main simulated geometry on the input 2. That means the input with the ID 1. So let's start by finding out how many points there are in the geometry by creating an integer, call it numpts, and use the endpoints function to look up how many points there are on our second input, the one with the ID 1. Next, we should check if we have points at all. So if our number of points is bigger than 1. Constraints only make sense if you have at least 2 points to connect with the constraint, so we're checking if we have more than 1 point. And if we do, we will create those constraints by getting 2 IDs. First ID will be our previous points number, so it's numpts -2. And our second ID, ID2, will be our current point number, that's the number of points, -1. Keep in mind, point numbers start with 0, so if we have 2 points, for example, in here, the first point will be the number of points, that is 2 -2, which will have an ID of 0, and the second one is 2 -1, which will yield the ID of 1. Let's get their respective positions. Call one npos1, use the point function to access it, like this, and let's just copy this here, paste it, switch the ID to 2, and call this one npos2 like this. Next, let's create a float containing the rest length, which in my case I will set to a fixed rest length, as I will assume that my string will have a uniform distance between each of those points that will be emitted uniformly across time. So that makes sense. Just set it to 0.025 like this. And finally, we are all set to create the constraints, which will be a primitive. So let's create a new primitive using the addPrim function, this time on the constraint geo, that is ID 0. It will be a polyline connecting the points with the ID 1 and ID 2. And I just realized that if I set my rest length to a fixed value, I can spare this point position lookup. This code gets a bit more compact like this. Now we need to set a few attributes in order to configure this primitive as a constraint. 5 attributes to be precise, starting with the rest length. We're going to do that using set prim attrib rest length on our newly created primitive. We're going to set it to the value stored in rest length. Let's just copy this here, paste it, and set the rest length origin, rest length orig, to the same value. Let's set the type attribute, which specifies which kind of constraint this is, to be a distance constraint. That's just a string configuring the constraint. Let's set the damping of that distance constraint to, say, 0.01, and finally the stiffness to a rather high value, for example, 1 billion. So a 1 with 9 zeros, like this. And that's our code for creating that distance constraint. Again, we are looking up how many points there are in a geometry and check if we have more than 1 point, so at least 2 points. Then get the idea of the newest point and the idea of the point created before that. Set a rest length value, and then create a new primitive, adding those 2 point numbers here to the polyline we just created, and then setting a bunch of primitive attributes which configure the constraint. Let's copy our geowrangle here, paste it, and wire it up into the merge too, and let's use this to create the bend constraint too. So again, first thing, we check the number of points, and then check if we have more than 2 points. Again, for a bend constraint, I need at least 3 points. Let's add a third ID to this by copying this line. ID 1, 2, 3. So the 3 newest points here. We don't need a rest length here, but we'll create a new primitive, being a polyline, spanning ID1, ID2, and ID3. Set the rest length of our newly created primitive to 0 for a bend constraint. Same for the rest length origin. Set its type to be angle. The damping can remain at 0.01, and let's set the stiffness to 0.1, like this. As usual, these are values that I found out by tweaking and reverse engineering some of the standard default vellum constraints. The only thing left to do here is, with our rest length set to 0.025, is to set our p-scale attribute on our individual particles that get emitted accordingly. And let's do that before we do all this by just sealing this gas intermittent solve just to be sure, wiring this in the particle forces slot that will be executed before this slot here. Let's cut this connection here and pipe in a pop wrangle with the simple expression p-scale equals to, let's set it to half of our rest length, 0.0125. Let's save this and keep our fingers crossed, just disable the point ID and hit play. And you can see a string appearing there and laying down on our collider, on our floor. Let's stop this for now. And the last thing I want to add is this jitter avoidance mechanism we talked about last tutorial. So to all of this here, let's wire in a last merge, and we're going to set up our particle jitter avoidance in here, consisting of 3 nodes. And while I perfectly could use the same technique I've shown in the last tutorial, in here I want to modify it a bit and check if a given particle has been below a velocity threshold for a given amount of frames, and if it has so, just set its mass to 0, which will exclude it from any simulation and just be sticky. Of course, I could instead use constraints, as I've shown previously. This is just a quick shortcut method that'll work too. So let's use a pop wrangle first and check if the length of the particle's velocity is smaller than a threshold. Let's use 0.02. That worked well in my case. And if it is so, we're going to increase an integer, call it a stop, and increase it by 1, like this. Next, drop down a pop group. Call this one maybe pin stopped for pin stopped particles. And let's enable the expression in here. So I want to check if the stop value that I increased here is, say, above 12. So if the particle has been slow for more than 12 frames, it should be in the group, like this. And finally, let's use another pop wrangle, limit this one only to the pin stopped group here. And if it is in that group, let's set its mass to 0, like this. And that's it. So this looks more elaborate than it seems. Let's just cross our fingers and see if this simulates. Save this and hit play. Let's stop that here and check by middle mousing on this. So yeah, that seems to work. We have a new parts group, a pin stop group, and our trusty vellum source. So let's head up one level and talk a bit about how, on the one hand, we can import this geometry here. So in our .NET, let's just select this vellum object 1 here, just copy this name here, head up one level again, paste that in here, highlight this. So we now have the simulation data in here, and we could, for example, drop down a wireframe 0.0125 as our radius, wire this in here and highlight it, and have our solid wire here that we're laying. But on the other hand, let's talk a bit about how you can reverse engineer those vellum constraints. So what I did here to figure out how to manually set up those constraints and which primitive attributes are needed and how many primitive points we will need for those attributes, what I did was I created a line, gave this bit of a subdivision here, and then just wired in our vellum constraint, set to string in our case. Wired this in, and then appended a null to the constraint output here. Highlighted this null and head to the geo spreadsheet here. And in the primitives here, you can see that the string consists of 2 different primitives and 2 different constraint types, the angle and the distance constraints here. So what I did is I blasted away any primitives that were not, in this case, let's just take the first primitive here. That's the first distance constraint. Check delete non-selected, which leaves us with this constraint here, so I can middle mouse on this. See, I've got 2 points, 1 primitive, that's the constraint, which got these attributes here, these 5 attributes. Let's do the same thing for our first angle constraint, which is primitive number 31. So copy the blast node, set the group to 31, and have a look at this. Again, 5 attributes here, but when I middle mouse on this, I've got 3 points. So this will be 3 points. Let's just have a look at this. You can even see that in the viewport here when I hit H to home in on that. I can see those 3 points are connected by a single primitive here. So that's how I reverse engineered those few constraints here. And you can do the same thing with all the other vellum constraints. They are basically just primitives with a certain attribute written onto them. But let's get rid of all this and have a look at our setup here, which is the basic silly string emission. Again, this might not be the most practical way of setting this up, but it shows how to manually create those constraints. And when diving into the .NET, I think one major takeaway here is that you can easily hack the vellum source in here, in the constraints emission, by just adding those 2, and let's color them green, those 2 group nodes here, which is just a trick I basically stole from the pop source. So let's head up one level, marvel at this beauty of a DOP tree, scratch our heads at why DOPS is the way it is, and see you in the next tutorial. It's cheers and goodbye.